I want to talk a bit about distributed file systems. I'll try to speed up, and I'll definitely stop at 5:15. Very briefly about GFS. If you guys don't ask any questions, I may be able to discuss all slides. It was just a question. If you don't hit chapter 12, do we still have to study chapter 12? Yes. I'm nasty. Or you can come back to class tomorrow, but that's not going to save the day, right? But these are actually simple things, so I'll gloss over a couple of things that are more interesting. I'll put emphasis on the most important things. You got to realize that all the hard stuff has already been discussed. Okay, so I really just want to talk about things that are more or less interesting. This is kind of interesting. I thought it was interesting. If you take a look at what happened in distributed file systems from an architecture point of view, you really had this strict client-server behavior. In the sense that you had this kind of remote access model. Everything stayed over here at the server, and you had a client that was sending requests to the server, do this, do that, and you could get a response back, right? Now, there's also the upload-download model, and this is, I think this is even before your time. I'll just admit it. When I was young, we did this. You were a client over here, and you went to another server, and you said, hey, give me that file. You fetch it with FTP, you put it on your local machine, you did whatever you wanted with that file, and you upload it, okay? And of course, this is not safe at all, because other people could be working on this thing. So this is a really old-fashioned model. Okay. So I turned young again, and it's for you to discover when, okay? I'll come to that in just a minute. Now, let's take a look at NFS. How many of you have heard about NFS? Very good. How many of you know how NFS works? A few. This is how it works. NFS is not a file system. Okay, so that's one thing you'll have to learn. NFS is just a mock-up that uses existing file systems. And by an existing file system, I mean a locally available file system on the machine that you're trying to access. NFS is basically one big set of access protocols. And this is basically the architecture that it uses. It has a client, and you have NFS support inside of the machine. That's not necessary, strict necessary. If you go out into all kinds of Linux boxes, you can see that there are user level as well as kernel level implementations of NFS. But let's just go for the simple one, namely the kernel level one. Here's your system call layer, your traditional file system calls. Many operating systems now implement the so-called virtual file system. Basically, it gives you a standardized interface to all kinds of file systems. And then you have a local file system. And what NFS does, it inserts an NFS client between this interface and when it actually goes out on the network. So if you're a client over here, your call will go over like this, over the network, is received at the server side, and this is where the interesting part comes from. That thing hooks up to the standard interface for the file system and operates on this local file system. And that's why NFS is not a file system. And if you then wonder, if you dig into NFS and to see what kind of things it should support, notably when it comes to security, you will see that it has gone through a lot of trouble to actually support the relatively simple Unix model of file security, as well as the more intricate, but more, you could call it advanced, model of Microsoft. And by now you should then understand why NFS has to do with both, because it has to support both types of local file systems, which is kind of nice. So this is what I just mentioned. The virtual file system provides a standard file system interface. And is NFS actually a file system? The answer is no. It's just a bunch of access protocols. This is an interesting table. No, you do not need to learn this table by heart. But where is the diff? So you have version 3, used a lot. Version 4, by now maybe used more than version 3. I wouldn't dare say so. I don't know. It's a guess. I don't know. So what's the diff between version 3 and version 4? Why do you say that? Because you know it. Can you see it?
Because it allows open and closing of
Which are definitely stateful operations. Yeah, that's where you see the difference. So where does this difference come from? Version 4 should be more advanced than version 3, shouldn't it? And I'll be a bit provocative. They went back to stateful servers? He said security. Not a good answer. Not this time. Yes?
They wanted to have a more file system-y and with more access control.
No.
No?
No. And of course they wanted that as well, but that's not the reason. You're not certain of your answer, otherwise you wouldn't say it like that.
Because recovery is now fast enough to provide auto-rented system.
No, but you're getting close. If you have a complete stateless system, what does that mean? Completely stateless system. Can you do this in a completely stateless system? You cannot. You're handing out your files to this client over here, who in his younger days was using FTP. You get the point?
Yeah.
Yeah.
You mentioned it already earlier.
Exactly. Thank you. You remembered very well. So, hey, this old guy over here is young again because he's using NFS version 4 for scalability, because if I now go to my NFS server, he'll say, here, here's the file. I don't see this as an application, but it's handing me out the file and it's registering, Martin has the file. It's doing whole file caching, for example. Something like that. And I can do local operations on my file. And why would I want to do this? For scalability purposes. Because suddenly the connection between the client and the server is a wide area link. So here's the file, play with it. I'm still in control and I know you have it. You can do that only with a stateful system. If you have a stateless system, you can hand out a file, but hey, the server's not going to remember you and it just lost control over the file. Or it says, well, you're not going, here's a file, but you're not having any control over it. So that's not going to work. And that's the reason why they moved to stateful servers. Okay? It's as simple as that. I'll skip this one because you want to talk about this one. So here's the Google file system as actually a very interesting file system. And I've simplified things a lot. There's a lot to say about this. But hey, what does this thing have? A master? That can never scale. Okay, so let's see how roughly, I mean there are lots of gory details on how this works, of course, but just to touch the surface of the Google file system. You have a client over here, and what it does, it contacts a master, hey, this is a centralized solution, right? It says, hey, I need a file name and a chunk index, and you get back a contact address. Things are called differently in GFS, but that really doesn't matter. And what basically happens is you have file systems over here, and these guys replicate and distribute things a lot. And basically what you're getting back is information on which chunk server you should contact, and it's the chunk server who's actually going to give you back the data. So the master is really here in control of also telling the chunk servers what they should do. Scales like hell. Also, for a very simple reason, most of the Google file system is, well, I wouldn't say read-only, but is mainly reading files instead of updating files. And it works like hell. So what they do is they divide files. This was in 2004 5 or 6. I'm not quite sure what the status is at the moment. In 64 megabyte chunks, and they distribute and replicate these chunks across many, many servers. Okay? The master maintains only a file name chunk server table in main memory for fast lookups. So this is the only thing that the master does. Minimal I/O, files are replicated using a primary backup scheme, and the master is kept out of the loop. Works for Google. It may not work for databases, but it works for Google. Okay? Yes.
What if the master crashes?
What if the master crashes? What would you do?
I would put a header on each chunky server that has kind of his local table, and if it comes up and the master contacts him and says, "Give me what you have," he gets back the first header thingy, puts it in his local table, and serves back up.
Maybe something like that. Because I don't know exactly what happens when the master crashes, but because the master has no I/O, I would say, well, you know, that stuff that the master has must be information that is easy to retrieve again. So the master should be allowed to crash, that's obvious. It doesn't want to go to disk because then you would lose the efficiency. So the whole idea would be that this information is pretty stable, actually. Okay? And that should be easily retrieved. And what you can imagine is that that information is actually maintained here, and then when the master comes up, say, guys, what do you have? Just fill my table like hell. So basically, it's just a main memory table, and it acts like that, and you just go to that. So I think it should be really easy to recover this thing. Okay? No primary backup for the master, I would say. Yes?
There's no going for the disk or code what?
Because the master maintains this file name chunk server table in main memory.
Why not in disk? Just performance? Why?
Oh, because of performance. Yes.
They don't.
Do you know how much a disk access costs?
SSDs? Why don't they use SSDs?
Because that's still slower. But that's a good question. So why don't they use modern disk technology? Okay. They may be using that actually now. I don't know. Maybe as an extension of the memory. But hey, you know, memory's nothing. You know, we have 96 gigabytes of main memory machines over here. But that's not the issue. What I wanted to say is that there's actually research out there that talks about a complete data center using really faulty SSID disks for the entire data warehouse. And if you just have enough of these things, it turns out you can build a really, really robust machine. Okay? Yes?
The other thing is, if you have it for what they do, if those tables are pretty stable, okay, it works. But if you have a lot of writes, comparatively a lot of writes, you will be swapping SSD.
Yeah, but you would expect that it's mainly read operations at the master. But it's still, yeah.
If you say Google size, and you, for example, have 256 gigabytes of memory, something like that, put it on 226 gigabyte SSDs. Well, on the one hand, that amount of memory is pretty cheap. On the other hand, well, you have to do like one of the SSDs for
One thing that is, what the policy of Google is still to use relatively simple machines. But basically, I mean, we could reason why they would or would not use it, but I don't know the strict answer to that. Okay. I'll skip this one. Did I put so many slides in here? Let me. Oh yes. No, I want to discuss this one. File sharing semantics in a distributed file system. You have to realize that if you have a non-distributed file system, you can have really simple semantics. What you normally do, guarantee in a non-distributed file system, is that you always can read the most recently written piece of a file, right? It has pure serialized semantics. Let me put it that way. We call it Unix semantics, by the way. We could also call it Windows semantics, provided Windows behaves the same as Unix. If you have a distributed system, you may get something else. You have two client machines over here. You have a process that's first read a file and got a copy over here. So now it has these two data chunks, A and B. And then let's say it writes C, but it keeps this over here. And now you see that process B will have different information than the client A. Okay? This is just inherent to any distributed system. Yes?
I don't see the problem.
Oh, yes, you do. You should.
Basically, the problem you have there is fully induced by latency. If you
Which is enough.
enough, but you can have the same latency on a local system.
What I'm saying is that in a local system, you will generally guarantee that you always read the latest right, and you will not be able to guarantee that in a distributed system. And that's because the latency on a local machine can be guaranteed to be so low that when you do a read, you will synchronize until the write is completed. Got it? Not in a distributed system. And that was the whole thing about keeping things consistent with sequential consistency. Now, why am I telling you this? Because what they did in practice is the following. You want to have Unix semantics. A read operation returns the effect of the last write operation, but there's no such notion of a last in a distributed system. And yes, you can implement this indeed with remote access models where you don't have any replicas of the files, but then you'll incur perhaps lots of synchronization costs. So people thought of building transaction semantics, and this introduced transactional file systems. File system supports transactions on a single file. Okay, that kind of works, and you can optimize on concurrency and whatnot. It's generally considered to be expensive. And this is what they implemented for a very long time in NFS version 2, I think it was heavily criticized because it was the last winner takes it all. That means that it could happen that you were doing a write and that you would be overwritten because there was a concurrent write going on. Tough luck for you. Now, how can you address these problems? You can do this the Coda way. Coda is actually kind of interesting. Coda, by the way, is being shipped as a standard file system with Linux. Okay, it's a very old file system, dating from back in 1986. Watch this. And do I have a more intricate scheme? I don't know. Let's stick to this one first. You have a client over here. You have the server over here. The client asks for the file and gets a copy of that file on its local machine. And it starts a session on that file. Okay? In the meantime, there's another client over here that wants that file as well and wants to write to it. So it's going to do an update operation. That client also gets a copy of the file, writes it back to the server, and now the server is so nice to tell this guy, hey, what you have over there is no longer up to date. Okay? Then this client just continues with what it was doing and closes the file over here. No harm done.
What happens if we cut and can come to harm? So
You mean if this is also a write? The server will not hand out the write to this file, because then you would have conflicts. But Coda says, I warned him, but no harm done, which is true. Why? Because this client is assumed not to know anything from this client, so this is an ordering that could have taken place. It could very well have been the case that this guy was seeing a version of the file, and then later it turned out to be updated, okay? But hey, it really doesn't matter. Because what you saw was still consistent when you got it. In fact, it was even consistent when you finished your read. Oh, of course, in the meantime, somebody else updated it, but that doesn't have to hurt you, because the ordering could have taken place. you are not affected by that right, under the assumption that the two clients do not know something about each other. They do not depend on each other, notably through this file. Okay? So that's what Coda did. I basically already discussed this. Now, let's go to a more intricate scheme of Coda. Now, so let's try to push this a bit. Have your client again, does a read, gets the file. You have this client over here, opens it for a write, does an update, does this, and the server is so nice to send an invalidation notification to that client. Okay? It continues to write, and now later, closes over here, continues to do its work, and now does a read over here. Now, again, let's assume that this guy over here does its work, wants to write the file again, and starts another session. Okay? In this case, it should have, over here you could get an invalidation, but I'm asking you, is this thing necessary over here? It says, I want to open it again, and it says, I will give you another file. I will give you the most recent version that I have. This guy over here says, I want to write it again. It says, okay, well, you already have the file, you can keep it.
So it basically follows, gets the file again, if and only if, the invalidation code.
So, but is this necessary?
In that case, yes. Because I can validate the code.
Is it strictly necessary? You said no? Why not?
Because like you said, if plan A is not connected to plan B, doesn't mean to upgrade something.
Right? It's still working on consistent data. Now the question is, how long are you willing to work with really old stuff? Well, at a certain point you want to update things. And that's when you will really have to go through the server to be able to work on the most recent stuff.
So unless you receive validation, you can open it from your actual.
If you do not get an invalidation, you can always open it from your cache. Yes.
But, how does the server know to send an invalidation to the client if it is not aware of how it's being opened by the client?
Oh, okay. How does the server know that it should contact the client if it doesn't know that the client is going to open the file? That's assuming that the server doesn't know that the client is going to open the file.
From its cache.
But the server does know it's going to open the file. What it does, in this case, take a look at this one. The client over here is just doing its normal work. It closed the file over here, right? And that led to a notification, a callback to that client over there. Now, this client over here says, I want to write to it again. And what it can say is, I still have the file. This is its version number. I'm not giving all that information. At that point, the server knows, ha, you got it? I'm up to date, but hey, you're still up to date as well because I didn't get any writes in the meantime. You can continue with what you have in your cache. Okay? So I am assuming the file server has full information on what clients are doing with their cached information. Yes?
The close is in response to the development.
No, it's always because you are supposed to close files after reading them.
And it's not that the server sends the validate and then client takes
No.
it. Okay.
No.
You could.
No. You could, but it's not necessary. This is system level stuff. Here, the application was done with the file. It goes through the cache. That's when the close is sent so that the server knows, okay, you're done. If I have an update and you do another read, I will make sure that you get the most recent value. And it doesn't strictly have to do that because that ordering could also have taken place, but you don't want to have this for too long.
But then I'm going to get what's the point
Exactly. So it's a politeness. No more than that. Okay? It could also be a warning, like you can use it in very different ways. At least you're now up to date that what you have in your cache is no longer valid. Okay? Then a final one on file systems. We'll talk about chapter 12 actually. This is how they did server-side replication in Coda, and it's a nice example of how you can do this in practice. So you have a bunch of servers, and what they're assuming is that a network partition could take place. And I haven't discussed this at length, but this is a realistic assumption. And what they wanted to do in Coda is nevertheless let the two parts operate independently and then see if anything needed to be repaired later on. Okay, so it's kind of an optimistic way of operating. So what happens is that they need to ensure that concurrent updates are actually detected. If you look at this, doesn't this look familiar to you? Every client has an accessible volume storage group. It's just a subset of what they call a volume storage group. It's called a local file system. Okay, it's called a virtual file system, whatever. It's just, okay, these files belong together. And we use version vectors. Oh, they're back. Okay, so you have a file F on J is K. That means that SI knows that SJ has seen version K of file F. You get the picture again. Okay? So if A updates F, then S1 and S2 could be this. And B updates, where is this over here, updates F on S3, then S3 becomes +1 + 1 plus 0 + 0 + 1. And then later they can, by just taking a look at the version vectors, come to the conclusion, guys, you may be out of sync. And depending on what happened, they can start merging the replicas again. And depending on what type of updates took place, they may actually get into conflict resolution. Conflict resolution has nothing to do with distributed systems. Distributed systems cause conflicts, but we leave the resolution to somebody else. Okay? I think that's about the only interesting thing I wanted to say about files. I know I'm not going to discuss 19 slides. I'm going to skip a couple of ones. Actually, I want to pick out only one. I only want to talk about one interesting thing. And it starts here. I want to talk about replication in web hosting systems. And I'm going to do a bit of a bashing, and but I'll not bashing Microsoft this time, which would be unfair. Bashing people who came up with protocols that are never used. Okay. So now just imagine, again, a big distributed system. It's called the web. We have lots of web servers. I always forget the number. I think I mentioned in the beginning that we have about 16 million DNS servers. I think we have 160, 180 million web servers. It's something like that. It's beyond imagination. Okay? And what you also should realize that if you take a look at the web, it is packed with caches. It starts with a cache in your browser. It starts with a cache on your local network. The VU has a cache. The ISPs have caches. There's a whole hierarchy of caches way up to the server where the actual content is served. Now, what you do with web proxy caching, and I'll just take it simple. Let's just take a local site, and what you do is you install the so-called Squid server, which is a web proxy cache, and it says, okay, I know that the clients within my local area network, let's say the VU domain, they go for web pages, all the requests go through this cache, what comes back I'll just put in my cache. And you often do not store dynamic content, but you store static content, images, for example. So the whole idea is that a site installs a separate proxy server that handles all the outgoing requests. Proxies are subsequent to cache the incoming documents, and then they have this infamous cache consistency protocol. First, always verify the validity by contacting the server, and you can also have age-based consistency that says the expiration time in my proxy cache is this formula. This is so-called aging formula, or based on an aging formula. It says, this is the time that I cached it, this was the last modified time, and what you notice is that when I cache it, minus when it was modified, hey, the older this document has been since it was last modified, the longer I will be allowed to keep it in my cache. Okay? This one is hard-coded into HTTP, and nobody uses it because it's useless. So, oh, I have something in my cache. Let me contact that server way over there, wait for its response to see what I have over here. It is based on the assumption that storage and bandwidth are the problem for an HTML page. It's not. Okay? If you have this with an image, that would make sense, but then you would even use the age-based consistency. Or, as I will just explain in just a minute, you use a content delivery network and it will tell you when it's out of date. Now, in the old days, people thought that going back to the server was expensive. So they did the following. They said, listen, instead of going way over there to that server, let me check my next door neighbor. And actually here in Amsterdam we have an excellent example. We have two universities. We have this university and we have kind of a campus over there. We have a campus over there and there's actually the science park over there. Okay? And just for the sake of argument, let's assume we have a proxy server over here at the VU campus and we have a proxy server at the science park. I would not be surprised that we actually have these things. Now, what would happen is the following. Let's say I'm a client machine here at the VU site. I go one way or the other, I follow a path to the proxy server here at the VU and says, I don't have this page. Because looks at this cache and says, I don't have this page. Tough luck for me. Oh my God, do I have to go all the way to that web server? No. I go to my next door neighbor. Here, my next door neighbor. My next door neighbor is at the science part and it asks, hey, do you have this in this cache? If not, maybe I can check that one as well. If not, hey, I'm disappointed, I go to the web server. Okay? That was the whole idea. Yes, they implemented this protocol and it didn't work. This is where my colleague Guillaume Pierre says, Martin, you can't say this because it worked. No, Guillaume, it was stupid. No, Martin, that's not the way to say it. Okay, Guillaume, what should I say? You have to explain what's going on. Okay, so now I'll explain what's going on. Why do I say it's stupid? Well, what are the assumptions underlying this protocol? That they access the same website, yes. What do you think of that assumption? So this is the VU, and this is the science park. You guys, you know, what? All connections are blatantly fast. They're good. I mean, they're absolutely good. That the others know it better than yourself.
Done some updating.
Yeah. Well, not necessarily updating, but they have read the file as well. Now, that's the only way how you can get it in the cache. Okay. And that's indeed the assumption. And if you translate this, the assumption is that the type of requests that are generated from over here are the same as from over here. This is not necessarily a bad assumption if you take a look at this community, because we have people from the VU and the UVA over here. Okay? How much do you guys have in common? You know an answer to that one? Well, that's good. Oh, okay. Yeah, Wikipedia would be a good one. Well, what I'm trying to hint at is that what you really have in common is not really that much that it's worth the trouble of maintaining two separate caches and having a protocol to check each other's caches. What makes a lot more sense is to rely on one of the caches along this path, where also the request from the UVA and the view pass, and instead of finding that stuff, if you can't find it in this cache, go to that cache, you will find it in that cache. And it turns out that they did indeed experiments on take sites and see what they have in common, and it's not that much that it's worth the trouble to have this intricate protocol for checking out each other's cache. Just relying on a cache towards the server. Works like that. Is that good enough, Guillaume? Okay. So it doesn't work. Let's take a look at, yeah, you'll like this. Let's take a look at at content delivery networks. So I'm going to talk about Akamai in just a minute, which is a commercial system. It's up and running there, and it works really well, actually. So if you take a look at replication and web hosting systems, I want you to now get into the following model. You are Akamai, and you are big, and big means that you have in the order of 10,000s of replica servers spread across the internet. And the business model is very simple. You go to ISPs, you hire storage and server capacity at the ISP, and you let your customers pay you more than you pay the ISP. Okay, that's. If you would do it the other way around, that will be kind of the stupid business model. So the first one is best, and you can actually make a decent living out of this. Yes.
Interesting addition, you can sometimes get the ISP to give it for free to you because they can actually save money with having you in-house or having you peer.
So even the ISPs could become your customers, and you can start driving the ISPs. Hey, you want me to be on your... Because indeed, the ISPs are then offered also a facility to keep the traffic local. And keeping traffic local means less traffic that you have to pass to this other ISP with which you have a peering relationship, and that's going to save you money. Thank you. I hadn't thought of this one. So the next thing that you need to decide is how are you going to replicate your stuff? Now, one thing that content delivery networks do is say, hey, we can help you first when it comes to availability. Okay, that's an obvious one. But they also say, we can help you when it comes to flash crowds. And what these web hosting services do, they effectively implement the feedback loop that I discussed way back when in the beginning. Okay? And they have 3 specific mechanisms, namely request routing. Where do I route my request of clients? They have consistency enforcement. I gave an example of that when I was talking about Globule, and I also talked about replica placement. Where do I place my replicas? I want to concentrate on these 2 in just a minute. Okay. These are actual traces. This is a very simple one. This is normal traffic at a website. We collected these traces a while back. And what you nicely see over here is this regular behavior, periodic behavior over 24 hours. Okay? And what you should imagine, how we do this thing is the following. You get requests in. Well, you just can't count requests. You take a very small time window, let's say a few minutes, and you count how many requests you have in that small time window. Okay? That number of requests appears as a dot. Okay? Because you can't count in just saying, hey, I just got a request, it's not going to give you any quantitative information. It's, hey, I got a request, I didn't get a request. So you take a small time window, and then you start making these scatter plots. This is also a trace collected, well, okay, let's just count requests per minute, something like that, over 2 days. Well, there's a big difference between these 2, right? And I deliberately ignored what's on the y-axis because that's not too important. It's the pattern that's important. So here you have this nice site, nothing's going on. Whoops, what's that? Suddenly lots of requests. And then, hey, they're gone again. Okay, I survived that one. Oh, oops. It goes down, down, down. Okay, this is normal. Oh my God. These things are called flash crowds. Okay, suddenly, out of nowhere, bingo. You just became popular. This one's also, this is, I'll get to this one in just a minute. This is also an interesting one. Whoops, hiccup. Okay? But notice that it's a different pattern than this one. Okay? And this one is really bad. So, okay, it's over a longer period of time, but if you would actually zoom into this part, you would see it as steep as it is drawn over here. It's all safe and sound, and then really, boink. You get so many requests, and you actually have recovery time over here, and then suddenly drops down and you have a number of these peaks. Yes?
The interesting part, in my opinion, is on the left, lower left one, see?
This one? Yeah.
It's not the black part above, not the white part there.
Over here. Yeah, you get...
Because you do not even get the lowest amount of requests per second does not even get below the average amount before it.
Uh-huh, yeah. Yeah. So this is a really nasty one. Now, if you do not provide mechanisms to sustain flash crowds, you wouldn't even be able to measure this because you would be dumb. Okay, it's as simple as that. And this is where web hosting services come into play because they say, we'll help you. And what they'll do is that they'll install replicas, and then they'll try to offload your traffic. And now you have to be aware of how do they do this? Well, the first thing that Guillaume actually was working on is, can I predict flash crowds? So what he did is, this is our usual way of working. We just take these traces, and we try to build predictors for these traces. And we succeeded. Per trace. You get my point. That's kind of useless. We tried everything. He said, there's no way. So to give you an idea how sophisticated he tried to be, I said, okay, I see this. Can I learn in these few moments in time? And you can build predictors that can really be fast learners. If you have simple predictors like just simple extrapolation of your traces, you can come a long way. But unfortunately, flash crowds are, I would always say, by definition, unique. Well, you can't predict what's unique. So we gave up. And notably because, also these ones, these are just plain nasty. Now what you can do with a content delivery network is you do place replicas, but how can you mitigate the request to these replicas? And now you have to start thinking, what is the real problem with handling flash crowds? Is it handling the requests? It's the bandwidth. And where does the bandwidth come from?
That's the thing. You often have to
Yeah, but so where is the real problem? It's not in getting the request, it's handling the response. Okay? So that's where the bandwidth consumption comes from. So what you can do is you can keep your origin servers installed in place, and instead of giving a response back, saying here is the content, and say go over there. Back, 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 back. So you have a couple of replicas installed, and then you can handle flash crowds by not giving response back, but saying go over there. Those are redirects. And if you do this right, then suddenly things can be spread across the content delivery network. You're still up and running, and your clients are satisfied. This is exactly what content delivery networks do. Okay? That works. Are these flash crowds, or are these denial of service attacks? You do know. That's the interesting thing. you can make a distinction between flash crowds that are often targeted towards a specific document or a specific part of your site, and a denial of service attack is really a denial of service attack with no purpose of fetching content. So it's arbitrary, and you can actually filter on them. And you need to filter on them to know what measures you should take. Because a denial of service attack redirecting to other replica servers is not going to save your day. Okay. So how do you build a content delivery network? How do you build active replication schemes? Or actually, I should say server-initiated replication schemes. Well, you do this by means of caches. And this is the way how Akamai did it for a very long time. And I have no idea how they do it now because they don't tell us. But at a certain point, they patented a certain technique. And the technique I'll explain to you just to give you an idea how you can use existing technology to actually build your own content delivery network. And if I would ever set up a lab associated with distributed systems, I would give you the following assignment. Build a content delivery network using existing technology. What's the existing technology? It's a DNS server, it's a Squid server, and it's an Apache server. And that's about it. You don't need more. And you do need to modify the DNS server. So let me tell you how it works. Every content delivery network still maintains this idea of an origin server. So what you should imagine is that you have, for example, Philips.com over here, where they have, let's say, just keep it simple, their web developers, they develop the Philips.com website. Of course, they will have outsourced it to a web development company. That's fine, but they work on their servers, and at a certain point, they upload the whole stuff to this origin server. This is where the contract starts with, let's say, the Akamais of this world. Now, I'm a client over here, and I'm looking for Philips.com, at least the index file. Okay? So far, so good. And let's assume this is a really fancy homepage with lots of images, videos, and God knows what. Okay? So what happens is I look up the file that is actually related to the index file of Philips.com. And I go through DNS, through the regular DNS system. And at a certain point, I will be redirected over here to this. I will get into the domain of Akamai. Okay, maybe after a specific redirection, but let's assume that happens, and one way or the other, just ordinary DNS resolution, I get to this origin server. It sends me back the home page of Philips.com. And now comes the whole trick. All these fancy things, they have very special URLs. They have URLs like special Akamai file.philips.com. I'm simplifying things a bit, but you get the point. They have names that are related to Akamai. And you need to resolve those names again. Okay? And this is very important. You need to resolve those names again to actually fetch the file. So you get back an HTML file with lots of these weird URLs that are referring to files that are in Akamai. So resolving those URLs brings you back to a DNS server under the control of Akamai and says, that file. Okay. Well, let's assume we're doing iterative DNS lookups. Then that server knows your IP address. You, as a client, says, I know to which server I should redirect you. And it redirects you to a CDN server, and this, for the sake of argument, is the one that is close by, because you're fetching, let's say, a video file. Okay? And what I said, I think 2 times during this whole course, if you have your server close by, that means low latency, but also higher bandwidth. So this server over here says, I don't have this in my cache. It's a Squid server. I don't have this in my cache. Let me fetch it at the origin server, because I know I'm part of the CDN. It fetches the file, places it in its cache, so the next time somebody else also looks for that thing, this CDN server says, hey, I have it in my cache. So how do you now do an update? So now let's say we update this huge video file.
can immediately send it to CDN server, CDN server, I'm anticipating that somebody can.
No, I want to use existing technology. You can do that. It's not. That's not the way that they do it. Nope.
You just check on the origin server and file exchange and so.
Nope. That's not existing technology.
Change that care.
Really? Yeah. You change the URL. That's the only thing you need to do. It was my URL anyway. I changed the URL. So I fetched it again. So I have to make the assumption that I do not cache the index file. Okay, so I fetch the index file again, which is just a couple bytes. Oh, URL. Go to the CDN. Go to the DNS server. Oh, that thing. Yeah, you should go to that CDN server. That thing, I never heard of that file. So it still has its old video in its cache. It will get evicted from the cache. Goes to this thing, fetches the file, says, hey, here's a video file. And they patented that. Clever, right? I thought it was clever. Yes?
If you change the URL, you might want to change the name resolution of the DNS CDN server.
Why?
And that is not because it has to know about that new URL.
Well, the only thing that this guy over here does, it doesn't really look at the URL. It looks at your IP address. It says, it's you again. I have to direct you to that one. It doesn't care about the URL. Yes? What?
I think the CDN DNS server is coming.
Is cuttable? No, it's not. No. Unless you can make the assumption that you can have a global CDN independent client IP mapper to CDN server.
What I would do is,
I have to stop. Okay, we'll take this offline. Wait a minute. Okay. Shit. Okay, I'll reveal one thing. I already prepared the exam. There are no questions about the last slides. I'll leave it up to you if you want to learn this. The last slides were about how you actually, if this is the static case, what do you do in the dynamic case? Well, basically you actually have to start shipping whole databases. And what the last slides explain is how you can avoid that. It's actually being implemented. I'll leave it up to you to decide if you want to study this. I'm not going to ask anything about this, but okay. I think I've been pressing it too hard anyway. Okay? Good luck next week.